hopefully I remember to delete the earlier video. Let's see. Oh, so I really want you guys, now of course, I'll let them get it if you're playing at home. Right? Okay. That'd be a neat video to watch. Let me just put that right there. First time I ever did that, I had it was like an Escher thing, looking through the bottle of water. So what we got going on here now is, let me just do it real quick. I've got this going on. I've got this. I've got this. So we just figured out this one has got to be, I just forgot, 2.875, right? Yep. So what do you think this one's going to be? 3.125. 3.125. So you can double check that. It's a straight line, so it's got to be symmetric. If it was curvy, it might not be the same distance on both sides. Does that make sense? Yeah. Because if there's a bigger slope and then it suddenly slopes out, it has to go further out on one side than the other. Yes, sir.
How do you do the intersect?
Oh, let's re-verify the other one. So second calc intersect.
Okay.
So let's say I want right here. Enter. Seeing how it's on the wrong one, so I just hit up to go to the other function. Enter. And then my guess is basically right there. Oh shit, what happened? What's your number?
Still on it, I think.
Oh, I see. The calculator is really being very, very patient with me. It's like, you can do it, come on. All right. So when you have three functions in there, you just got to be careful about making sure you're telling it two different functions. So there at 3.125. That's the other intersect, right? How are you guys doing out there? I see some pained faces.
Can we solve the intercept by setting the function equal to the number, like 23.5?
Yeah, you can. Sure.
Okay.
Yeah, you could do it by hand. I love it. Kick ass.
Okay.
But you can also do it in the calculator. Kick ass. So what does this mean? What would I let delta be? So epsilon was 0.5. What's delta going to be? So what was epsilon exactly? How did I use epsilon? I started where and I went what?
It started at
from
the 3 and then
I didn't start at 3. I started at 24 because epsilon is all about the y-axis, right? It's all about the output. So I started at 24 and I went 0.5 away, 0.5 away.
Oh yeah.
So now this is kind of backwards. Can you figure out what delta has to be?
1.25.
Yeah, because it's going to be the center is 3. So delta has to be 0.125. Let me let you absorb that.
What is delta again?
Delta is how close I have to be to my input, so that the outputs are all
in that zone,
closer than this in that zone. I like it.
So what does the 0.125 mean though? That's what you.
That means if I try to use this, will I be in this little area here? If I use this one, no, I'll be too far away. Will I be within 0.5 of the limit? No.
Okay, I see that. Like that 0.125 is like that's how far away 0.5 is. You know, I see that there's like a relation between the two, but I don't understand what the 0.125 is as a number. Like, what is it?
So if somebody said 0.1, what do you think is going to happen to this delta? In order to be within 0.1 of the limit, I'm going to have to be
0.125 what though? What is it?
Oh, there's no units on it. It's just how far away from 3 you have to be. The furthest you could be away from 3. So that all the inputs in here will actually end up as close as they're supposed to. And how close are they supposed to be? That close.
Okay, so the epsilon is the distance on the y. And
beautiful.
The delta is the distance on the x.
Exactly.
Okay.
I like it.
Okay.
Right? I like it. So I know, I got to say some things a few times. You never know how to put the words together, so it's going to make sense. But I think I just won a couple people over, maybe.
I got it.
So it's all right. So the proof says these are nice, but it's got to work for every possible epsilon, as small as epsilon can get. And any concrete epsilon you use, I can get 1 billion times smaller, right? Just think of the smallest number, now cut it in half. Oh shit. You with me? So the proof is much more powerful, of course, but this is good enough for like a concrete understanding of what the hell's going on. Hopefully. Right? So if I had the right limit, as people say I want to get closer and closer, I can always find a way to get as close as they want me to be. If I had the wrong limit, it's not going to work. At some point I'm going to be like, oh shit, I can't get where you want me to be. That must not be the limit. Yes, sir?
So the proof of this will make it so we don't have to keep calculating smaller and smaller
Yeah, to do it this way, to prove it, you have to go forever.
forever and ever.
And until you get to something called iota, which is the opposite of infinity. It's the smallest positive number, is iota. Right, so let that keep you up tonight. If there's a biggest positive number, sort of, is infinity, and we know it's a process, there's a smallest positive number, which is iota, which is itself a process. It's just 1 over in the infinite process. Wait, yeah, I like that. That's a good band name. The infinite process. Sorry. Maybe not. 1 over the infinite. Even better.
The infinite and the iota.
Something like
That's
that.
a band name.
All right, let me think. What was I going to show you? All right, so let's do this. Let's do this. Let's do the proof. Here we go. You ready? So we already kind of know the answer to this. In fact, you got to know what you think the limit is to get the proof going anyway. So we're using the same function. So if you start to read this through, don't freak out. We're going to go through this together. I just keep thinking, every time I hand a handout, I keep expecting people to just get up and just leave. No, wait, please. No, I'll explain it as best as I can.
Calculus is really hard, but I actually rather enjoy it.
Good.
Best if you don't look at the paper.
What's that?
Best if you just don't look at it. Just wait.
The less I look at it, the better it seems. I can take that. All right. So let's take a look at this thing. All right, little dude. Little dude. Is it there? What's it doing? Oh, good. Capture mode deactivated. Good. I almost didn't capture anybody. Yeah, the little capture button's awesome. So we try to leave it, just push careful. Alright. Alright, you guys all have this in. We can read along. Alright, so here's the same function we just used, right? That's nice. Good. So sort of know something about it. We know a lot about it already. We already did this first part. Cool? We did that first part. When we factored it, we canceled the problem. So just to remind you guys, we factored it. The problem canceled, so we're able to plug the 3 in, and we got 24. Cool. Right, so we know the limit is 24. We feel like the limit is 24. We feel pretty good about it. To officially prove it, and let me say this. I strongly feel we should do this, obviously, because we're doing it. We're not going to get as deep into it as you could. Just trust me. The minute you make your function non-linear, you get some funky-ass ways to do it. But I at least wanted to give you that little push of, here's how the setup looks. Here's epsilon and delta, which are used every damn where in all kinds of proofs of theorems. So I want you to get used to them now, right? And then we're going to do the easiest possible examples for them. I think in the homework I assigned a couple that might challenge you, just because I do that. But we'll see what happens. Just to get used to the setup, we're going to do the easiest kind of examples we can. So here's the official proof. This is what I wrote on the board last time. Some jerk comes up and gives us an epsilon. I want you to be within 0.5 or 0.1. You know? So somebody gives us epsilon. They were given epsilon. We have to find a delta. So if they tell me this is how close I want you to be on the y-axis, right? The outputs have to be this close. If you think that's really the limit, you should be able to do that. At some point, if that really is the limit, when you get close to the x value, your outputs better be getting close to the limit that you think it is. Does that just make sense? Because that's what a limit freaking is, right? If you get close to the x value, then you should be getting close to what you think the limit is, if it really is. That's really all this thing is. And I think I say basically that. We must find delta greater than 0. We have to find a interval on the x-axis so that we always end up with as close as they want me to be. So that's the concrete thing we just did. Now we're going to do it less concrete, more abstractly. So here's what it looks like abstractly. That says, what does that say? What is that value based on? Why is it always positive? Because it's based on
The
distance. Cool. So I want the distance between x and a. So that I want, how close to a do I want to be? At least delta away, right? Or at most delta, I'm sorry. At most delta away. So we're closer than delta. All right, so that's just saying I want to be a little interval around my x value, my whatever the limit's going to, the a. I want to find an interval around that so that all the inputs are really close to what I think the limit is. I should be able to do that infinitely, forever. However small this jerk makes epsilon become, I should be able to make my intervals smaller so I can always end up close. So the inputs have to be within some interval that makes the outputs that close to what I think the limit is. That's what that says. So I say here in English, it says that if L really is the number that f of x approaches, then we should be able to find an interval around A where all the outputs for those inputs in that interval are arbitrarily close to L. Close being defined by epsilon. Right? Epsilon defines how close it is here. Delta defines how close I have to be here on the x-axis. Okay, maybe. I love the looks. So you guys are like, yes, but you're like, yeah? This makes sense. I don't know if I'm trying to convince. If the limit really is L, if that really is the limit, then the function outputs have to eventually get arbitrarily close to it, don't they? I mean, if that limit really is truly it, at some point. It could be going insane, but at some point it's got to get really close. At some point. This proof, the feel of this proof almost feels like we're cheating. Once we do a few of them, you'll see what I mean. It's a construction proof. We're going to construct delta. So why does this make sense? If somebody gives me epsilon, what did we say? If they give me a smaller epsilon, what's going to happen to my delta?
It's going to get smaller.
It's going to have to get smaller, isn't it? So based on I'm going to construct a delta that is somehow based on the epsilon I'm given. And what I love about the way I decided to do this is once we figure out what delta is going to be from this proof, we're going to show that it is exactly what we did here. And some of you guys might realize, well, it's the math just doing it, but oh well, we'll see. So this side work is what people think is the proof, or they think is cheating or something. But here's the idea. Okay. All right. So, conjecture. We think this is true. And then I just note that if from this, A is 3, cool. A is always that x value we're approaching. F of x, of course, is the function we're looking at. And my L is 24. I just want to set those up. Now on the side, what I do is, so if somebody gives me an epsilon, I want this to be true. Let me just stop there for a second. What does epsilon control? It controls
Y.
Y, distance.
Good. So be very specific. I want what to be really close to my limit. I know it sounds weird.
Output.
Good. Good. Sorry, I got excited because I'm like, what am I going to do to make you guys say it? And you just said it. I want the outputs of my function to be this close to the limit. Yeah, you kick ass. You guys got it with me? Right? Isn't that what we just said? This is what we've been saying. So I start here. I say, let me just start here. Now watch, this is kind of cool. This is kind of cool. And you're all like, finally something cool, really? I simplify the inside. Is this cool? I mean, you guys, we can do this. And then we get 4x plus 3.
Yeah.
So it's 4x plus 12 when I distribute, right?
Yes.
And then I get this from here. Is this cool? I have 4x minus 12. I can factor a 4 out. Let me go back up here for a second. Let me make sure this makes sense. So let me show you something really interesting. When you get into a proof class, if you're going to do math, if you're going to be a math major, I hope to God I don't change your mind in the wrong direction. So when you do that, because this is kind of cool. We use this, WWTS means we want to show. We want to show. You with me? So let me make this concrete about what we got. I don't think I did that on this paper. If x minus 3 is less than delta, right? That's what it says, right? I just want to put the 3 in there for A. Then, let me just put f of x minus 24 is less than epsilon. Right? That's what we got to show. We got to show if this is true, then this is true. That's what we have to show to prove this. So what I'm doing right now is not a proof. Where did I start with the work I'm doing right now? I started with where we want to end up, didn't I? Which is why it feels like we're cheating, but what we're doing is we're constructing what delta has to be to make this work. So when somebody gives me an epsilon, this is what they want me to do. They want me to be within epsilon of the limit. That's what that says. Is that cool? They want to be and then when I work this out, what do I get here?
Epsilon over 4.
So look at the form of it. What must epsilon over 4 be? Delta. So if we let delta equal epsilon over 4. And somebody real quick, what is 0.5 divided by 4? Do you understand what I'm saying? Maybe. I kind of I never really thought about doing that before, but I love this. There's a concrete kind of feeling out. It's not a proof, because, again, you'd have to go forever until you get to freaky whatever the hell, iota bullshit. But you can capture concretely. So if epsilon was 0.1, what would delta end up being?
That divided by 4.
0.025. Cool, because you got to move it over 1. Good. I like it. You guys got it.
Yes.
So that is a method to react to the jerk that comes up. So we're ready ahead of time. And it comes negative 0.1. Divide by 4, 1, 2, 9, just go. Right? It's a method of saying I can react to the epsilon I'm given. I can just say, well, I just want to be this close then. For whatever epsilon you give me, I just have to be 1/4 as close, and that guarantees it'll be that close to the limit. So this is the side work. The beautiful thing is it will always work like this. You'll always capture this statement. So whatever's sitting there will be your delta. Right? Let me just make that's delta. Have you guys seen delta before?
No.
You should have seen. Yeah. Yes.
So if it's linear like that, whatever the number is out front.
Basically, I love it. If it's a linear function, but in this 4 will be out front, it'll be 1/4. And that can make sense. If it wasn't a very steep slope, then I can be really far away and still be close. But if the slope gets steeper and steeper, then I got to be closer and closer, exactly the same amount. So if the slope is 4, I got to be 1/4 that away. Well, the minute your function is not linear, who knows? All right, maybe. So then what you do, this is all side work. I still want to see it, but make sure that it's off to the side. You're not done. Now you can do the proof. Given epsilon greater than 0, let delta be epsilon over 4. We constructed that through the side work. Then, what are we supposed to show? What do we want to show? We always want to show if x minus 3 is less than delta, that implies that f of x minus 24 is less than epsilon. So, when x minus 3 is less than delta, bam, 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 and look at all this. Isn't that just that in reverse?
Yeah, yes.
So on one level, this is almost too easy to believe. You're like, I'm just going to do the same thing, just reverse. Yes. But you're getting used to the epsilon and the delta and sort of the words that you have to use in proofs. So your proof got to look like this. So you do all this, and so when this is true, then this is true. For what values of epsilon? Which values of epsilon? Only 0.5 and 0.1, or what values of epsilon? Any damn value of epsilon. It could even be big like a billion. That's stupid. But the important thing is it can be stupid small, right? No matter what value of epsilon, that works. So we've proven it. That's true. So if you have the wrong limit, if you put a 25 there, it won't work. It's not going to work. So let me see. You guys are like, it's easy sitting here and listen to you. So do that. Let's see if I did that right.
So once you find delta, you're supposed to do it over?
You're not doing it over.
Well, not do it.
It's just kind of a happy coincidence that the proof work is the reverse of the side work. It doesn't always work exactly like that, but our function is pretty simple. So what we're doing with the side work is constructing the delta that will work. And it's just kind of a nice coincidence for us that the work is the opposite of what we did over here, right? So it does feel like you're doing it twice, but oh well. The side work, you're making the delta that will work, and then the proof, you're showing that the delta works. Yeah. No. So the proof of this is this. This is algebraic manipulation, which gives us a number that, for funkier functions, that actually might not be right. This is the official proof. So you shouldn't really be factoring and stuff. The number I gave you is what I think the limit is. And if you did factor, you find out that it is 20. That is true. It's true. So the proof should work. The proof is everything we just did with epsilon and delta. That's the real proof. See how many of you guys are still with me tomorrow. Most teachers don't do this.
That's a Friday job for that,
Yeah, this Friday, right? Yeah. All right, so you got some time to think. If you leave, it's okay. Less homework for me. Oh man. Make sure we're on the right track.
That's sideways. Do we need to do that?
So again,
Do we need to do that sideways?
you have to, otherwise, what would delta be? Yeah. Again, though, somebody pointed out there's a shortcut for linear functions, but I do want that sideward done. There are some examples in the textbook about what if it's a quadratic. That's not really quadratic, right? It becomes linear. True? So what if it's a true quadratic? Then things get really weird quickly. The minute it's not linear, it gets weird. So there are some examples, and I think I signed one that's sort of like that in the homework. But I just wanted to see who would try it.
So after you found delta, you have to do the proof.
Exactly. Yeah. It's not official until you run through the if this, then this.
I get that, like, this is the reverse of this, but how do you go from this to this?
Oh, it's pretty much you just follow this. You're trying to recapture this function again, right? And you know that the limit, you want it to look like this. So you know you're going to pull that negative 24, and then whatever the hell goes there. Right? So even if you had to kind of like do this without having that information, you know it's got to be minus the limit. So you can just put the number there to make that actually work. Does that make sense? Yeah. But the nice thing is you got that work there, just backwards.
You do this? I don't know what I did though. It's kind of hard to follow how to set it up. Like once I got it set up, it was not.
Yeah, good.
So once it's all,
And now you can do this proof. This is the real proof.
I think it's what it lost.
At the end, you left the absolute value too, right? You just left it. You left the absolute value. Like the last line is like absolute value x minus 5.
Yeah,
The proof is all
I
this.
used the absolute
You have to say all those things.
and then because delta is the entire formula of absolute value x minus 5, you replace that including the absolute value with delta.
So I have to get to this right here.
Yeah.
This was really the only thing I could have got to.
Yeah.
X minus 5.
Pretty much, yeah.
Okay, so that's what your side work should lead you to. Which is good because again, it's always if you do take a proof class, you will realize how important it is for yourself and for the teacher too in the grade to write. Even if the teacher doesn't want you to, we want to show. This is really good to write for yourself. We want to show if x minus 5 is less than is less than delta, then f of x minus 20 is less than epsilon. That's what we want to show, right? That's what we have to show. So that's going to be the proof. Starting at x minus 5 less than delta, and showing that that leads you to f of x minus 20 is less than epsilon. That's the proof. Got it. People trying to come in here early.
That's like that person's worst nightmare. They just walk into class, the teacher's like, get out of here! And then they
That would be
just,
awesome.
they're so scared out there.
Oh, I said that after he left over.
Oh, did he? Oh, okay.
Do that.
I didn't look back, so.
Get out of here! If I was him, I'd just sit down and say, no. Do something. So you follow this pretty much. Given, so that everything that gets started is somebody giving me an epsilon greater than 0, right? So that dork just wouldn't come over, then everything would be fine. We let delta equal what? What do we get?
E over 2.
Epsilon over 2. Epsilon over 2. Cool. Then, if
Are we
X-
supposed to write it out in words?
so
Are we supposed to write that out in words, or can we just do the
I thought we were doing the equation.
that
a
leads
proof
to it?
has words. Math actually does use words when you get to real math. Right? You can't always just now. It's built on the backbone of cranking out computations, but proofs in higher math requires you to explain what the hell's going on. So yeah. If you look at any journals of mathematics, look at some proofs, you're going to see a lot of words. But of course, we use a lot of symbols too. I'm using more words than normal, just because we don't know all the symbols. Given epsilon, let delta. Then if x minus what? 5 is less than delta, what does that have to lead to? So if x minus 5 is less than delta, I'm sorry, we don't have to say it. If x minus 5 is less than delta, that means x minus 5 is less than what? What's delta? Epsilon over 2. And we can immediately multiply the 2 back, right? We basically just do all of this in reverse. But even if we didn't have this, I want to try, let's pretend like that's not there. I'd multiply the 2 up because I know, what did we say we had to show? Where'd it go, Jeff? Here it is. We have to show this, so I know I'm going to get epsilon by itself, don't I? So, okay, I got to multiply the 2 out. So it'll be 2x minus 10 in there. Is that cool? Are you guys understanding that you can pull positive numbers inside and outside of an absolute value? You guys should know that. All day long. Absolute value doesn't care because it's already positive. Who cares? So that's why I'm allowed to put that in. You guys also know, this might come in handy on some homework, that the absolute value of x minus 5 is the same as the absolute value of 5 minus x.
Yes.
Of course, right? Because in general, the only difference between them is a sign, and the absolute value of x is both positive, so they're equal. In the homework, there might be some that say 5 minus x. Well, you just turn the damn thing around to make it look more like the proof, right? Because you're allowed to. It's inside of an absolute value. Who cares? Okay. And now, so now the next step is, I know I want the minus 20 to be here, right? Because that's the limit. So then how would I write this so there's a minus 20? What would I have to put here so that it still equals minus 10 altogether? Plus 10. You guys see what I'm saying? Now, of course, you're never going to be, without this. You can just see that exactly is the same step they had here, isn't it? So you have this just to work backwards, but you could still do it even without this. And then I'm trying to recollect that function. Get that function to show up again, right? So this would be 2, if this is x plus 5, I want to have an x minus 5 on the bottom, right? So I better multiply top and bottom by x minus 5. And again, that's just this step here in reverse, right? But again, why did I do that? Because I know I want to have this show up again. I need an x minus 5 down below. I better multiply the top by x minus 5. Kabam. And now that becomes my function. That becomes 2x squared minus 50 over x minus 5 minus 20 less than epsilon. So, if I let delta equal epsilon over 2, if I'm that close to 5, my outputs will be that close to 20. Done. That's what I needed to show. Given any epsilon, can you find a delta so that that happens? Yes, we can. We just did it. Bam. Done. I like it. So on one level, it seems like you just rewrite and you're like, rewriting. It's too easy. I'm just rewriting what I did over there. On another level, I want you to realize the functions we're using are stupid easy, because if I make the function one little bit harder, the whole thing gets really weird quick. So I can't get far away from linear functions. I can't. Or else it's really out of our control.